Hi, this is ET350 lecture 16. And so today what we're going to be talking about is percent speed regulation for induction motor and the power flow induction motor. And the last part of this lecture we'll be talking about is how do you measure power in a three-phase device? So this could be for an induction motor or synchronous device, any three-phase device. And what do we have here? Well, we know we have Y and delta. And so we'll look at a bulletproof way to measure power or three-phase power in Y and delta configuration. But then with some issues with getting the currents and voltages, it might be more convenient to get the line current and line-to-line voltages. So this is kind of a trick where you can measure power in a total power for three-phase device where you have a √3 here and a power factor. We'll talk about this. Now this has some assumptions of balance and knowing this power factor. And so there's this other method called the 2-watt meter method. And this 2-watt meter method doesn't need to assume balance, and it can be used for Y and delta. Actually, same with this one. We'll look at a simulation, and we'll even look at how do we compute the apparent power. Okay, so let's begin. So speed regulation. So speed regulation for induction motor measures the speed difference between a no load and a fully loaded condition. And so this is the definition. So it's a unitless number. It's the no load minus the full load over the full load. And so what does the no load mean? So it's the speed of the motor, right? Under no load. And if we remember our induction device, you have your stator, you have your three-phase coils, and it creates a synthetic magnetic field that spins, and the rate at which that spins is omega s. And at no load, the rotor gets currents induced and actually spins, and it spins very close to the synchronous speed, not quite, there's a little bit of slip, and omega no load is very close to omega s in that no loaded condition. In the full loaded condition, the omega m slows down because now you're applying some torque, some resistive torque to it. And this is the speed at operating condition, right? And so if you have a smaller percent speed regulation number, you actually have a better performing motor, right? And typical induction motors are in the 3 to 6% range, right? And so what that says is that the speed relative to no load and fully load is only 3 to 6%. It means it doesn't slow down that much, even as you add full load under the normal operating conditions. Okay, it's just another spec, a metric. So that way, if you are amongst engineers, then they're talking about, well, what's the speed regulation of the motor? You're not like blindsided. I don't know what you're talking about. Well, this is what you're talking about. It's like, how good does it maintain speed? It's similar to percent voltage regulation for a transformer. How good does it maintain voltage? And look at the equation, it's very similar. Okay, so let's look at the power flow in an induction motor. So the power flow is very similar to how we looked at the power flow of a DC brushed device. You have your input power, you have your output power, and then you have all your losses, the electrical losses and mechanical losses. The electrical losses can be the copper in the three-phase stator, they can be the eddy current losses in the steel, and it can be the aluminum losses in the rotor, right? And so it's just P in minus P loss equals P out, where the losses are all the electrical and mechanical losses. This is like the losses in the bearings and the windage and all that good stuff. The other thing, just another concept, is that you could think of these three powers as the power that goes into the rotor, right? And this power that goes into the rotor is proportional to the power that's lost in the aluminum, right? Okay, because the I squared R losses due to aluminum. And so P loss to the aluminum rotor is equal to S, which is that slip number, right? Times this power to the rotor, right? So at 100% slip, at 0% slip or no slip, there's no induction. The speed of the motor or rotor is going at the same exact speed as the synchronous speed or the magnetic field. Okay, if that's the case, you get no, by Faraday's law, no d phi dt. If you get no d phi dt, you get no current. If you get no current, you have no I squared R losses, and you have zero power loss in the rotor. Now, if you have 100% slip, now you're not spinning, you're stalled, and these two guys are zero, right? No mechanical losses, no output power, right? And when that occurs, now all the rotor power is going directly and burning off as I squared R losses in the rotor, and it's just wasted heat. So the synchronous speed is going round and round and round, and like you're holding the shaft here and you're not letting it move, right? And this rotor is just getting hot. That's all that's happening, okay? So I hope this isn't too bad. This is just the power flow. Where's the power going, right? Just the power accounting for an induction device. Okay. All right, now let's go to the main topic. And this is looking at measuring the power in a three-phase device. So for a three-phase device, let's look at Y first. And for Y, what do we have here? A neutral and three terminals A, B, and C. I have line currents IA, IB, and IC. And I have line to neutral voltages AN, BN, CN, plus minus, plus minus, plus minus. And a bulletproof way to measure the total power is just to add them all up. VAN times IA times its power factor, plus VBN times IB times its power factor, plus IC times VCN times power factor, right? And all these are RMS values, right? RMS power factor, okay? All right. Now, if everything is balanced, we could take 3 times one of the phases, right? And just add them all up. And so, for example, you could take the A phase. Could have been the B or the C. Now, the issue with this is that sometimes this neutral is inaccessible. These are the stator coils, and this neutral could be buried inside the motor. You don't have access. That means you wouldn't be able to get these voltages. You could get these currents via like a current clamp or something, right? But these voltages would be tricky. Okay. So what about a delta? A delta looks like this, right? You have your delta connection. The line currents would come in IA, IB, IC, just like these. But now notice the difference. I have line-to-line currents and line-to-line voltages, unlike this. But the concepts are the same. I could get the total power via a bulletproof method of line-to-line current times the line-to-line voltage times its power factor for A, B, and C. No problem. If it's balanced, all these are the same impedance, same, three-phase power supply, all that stuff, then the total power is 3 times a single phase. And you could have used the A phase here or the B or the C individually. It's just 3 times that. Now, this current here is difficult to measure. It's hard to get that line-to-line current. This is usually buried in there. You usually don't have access to this. And so that's an even harder problem. Like sometimes you might actually have the neutral like terminated out, but this one, usually you don't. So you can see that both of these are bulletproof methods, but you have some practical issues with trying to get either the line-to-line currents or the line-to-neutral voltages. So what's accessible? The line-to-line voltages and the line currents. Well, we have an equation for you. You can also estimate the total power by this equation, square root of 3 times the line-to-line voltage times the line current times its power factor. But you have to actually assume 2 things. You have to assume that the power factor is known, and you actually have to assume that it's balanced. Now, the nice thing about this is it could be Y or delta, doesn't care. And if you use the RMS of this times the RMS of this times the power factor times the square root of 3, you get the total power. Now, you might be asking, well, why root 3? Why not 3? Okay, and why do we have to be given the power factor? Why can't we just do the cosine of theta VLL minus theta IL? Well, I'll explain why. So let's look at why this root 3 is what it is first. Well, let's go back and let's look at that y. I'm going to hold on to this, right? Now, power total equals 3 times power 1 phase, no problem. And remember, power 1 phase is going to be the line current coming in times the line to neutral voltage times the power factor. Good. And if you recall from your 3-phase Y delta conversions, the line to line voltage from here to here is bigger than the line to neutral voltage in magnitude by the factor of root 3. And so you can solve with this and you get the 1 over root 3 and you bring it in. What do you get? I line times V line to line over square root of 3 times the power factor is the power of 1 phase. And I can plug this in here. Notice I get a 3 over root 3. Well, 3 over 3, ladies and gentlemen, that is root 3. And so you can see that I get the same equation as this guy here, right? So that's where the root 3 comes in. Okay, and again, these are convenient to measure. Current clamp, voltage probe, easy, don't have to dig into the internals. Get a wire delta, yay. Okay. Now, why must you be given the power factor? Why can't I just take the power of the cosine of the voltage and current difference here, right, of those phases? Well, this is why. Well, remember that the power factor is cosine of theta V line to line minus I line to line within a phase line to line, yay. Or it's the cosine of theta V line to neutral minus theta I line to neutral, no problem. These are okay. But you can't assume that this power factor is equal to this. That is not true, right? We will be able to use this, by the way, in the 2-watt meter method, a little foreshadowing. But you can't mix the phase of the line to line minus the phase of the current line to neutral because of the 30-degree phase shift, right? Remember, the line to neutral and line to line have a 30-degree phase shift plus or minus depending on the positive or negative sequence, and that'll mess that up, okay? All right, let's keep going and introduce the 2-watt meter method. In the 2-watt meter method, we're going to list some benefits. Conveniently, we can use, just like in the previous example, the line-to-line, line-to-neutral voltage. No neutral is needed. Yay. No assumption for balanced. In this one, because you're only measuring one phase, you had to assume balanced. In this one here, right, it has to be balanced. Okay. You can compute the power factor from theta VLL minus theta ILN. Well, I got to be careful. This isn't like the true power factor. This is, I should be very careful about this one. It's not quite the power factor, but you can use this phase difference, okay? And you'll see why later. And it's okay to mix in this new case. And here's the setup. If you have a motor, and it can also, I should also mention, it could be connected as wire delta. You have A, B, C here, and you can have IA, IB, and IC. Now notice we don't even care about IB. It's just IC and IA and IC. And now be very careful about how we're measuring the voltage. VAB plus minus VCB plus on the C minus here. So both the negatives are attached to the B. And this is the total power equation. It's the RMS version of IA and VAB times the cosine of the phase difference between these two voltage and currents. So this is okay now. Plus RMS of IC and VCB times the cosine of the phase difference between this voltage and current. That's easy, no problem, okay? Now, what I want to do is show you why that works, and we're gonna have to do a little bit of a review. And you've seen this before in your previous classes, but let's review it again. Remember, the complex power is just I times V with this complex conjugate. Well, maybe you forgot what the complex conjugate was. The complex conjugate, it's like dirt simple. If you have a phasor, I, the magnitude of the phase, the complex conjugate is just I, the RMS, and the negative of the phase. All you're doing is put a negative there. The reason why you put a negative, because you guys all know that the complex power is just IRMS VRMS times theta V minus theta I. It just handles the minus in the negative theta I there. Okay. And we, of course, unit of volt amps. Now, the length of this is just IRMS VRMS, right? And you have this, right? Theta V minus theta I is the angle. IRMS VRMS, or this S, this without a vector. So notice I put a vector there, is the length. Good. And what's the real power? It's the it's right here, the real axis. P equals IRMS VRMS cosine of theta V minus I, and then Q is IRMS VRMS times the sine of theta V minus theta I. No problem, right? This should be a review, shouldn't be too bad, right? We are going to use these facts in the proof of this guy right here, right? Okay. So let's have a setup. Let's just choose Y. Could have been a Y or delta, but we're going to choose Y for now. It just makes it a little bit easier to show us in this proof. Now, again, I have the same setup. IA, B, and C. Boom, boom, boom. I have VAB, VCB. Same thing. Now, inside, it's all connected. All the three-phase coils are connected in Y in this case. So I have ABC, VAN, VBN, VCN. Notice no neutral connected. Nothing here. Good. It's all connected to each other, but nothing else. We know that if we want to get the total complex power, then we can just add up IAVAN with the asterisk here, just like this, and do it 3 times for these guys. This is the bulletproof way to do it, okay? Now, what we're going to see, can we go from here to this? Well, we can use KCL. This current IB is equal to the negative of this one and this one. Good. This voltage here, VAN, is equal to VBN plus VAB. Good. This voltage here, VCN, is equal to, look at this, minus plus. So I have minus plus minus plus, VBN plus VCB here. And I'm going to take these 3 things and plug them into this equation. What do we get? We get IA star times VAN, which is this guy. That's not too bad. We get negative IA, negative IC star times VBN. That's this guy. Good. And we get IC star times VCB plus VBN. Good. And here's what's really nice. Look at this. These cancel out. IA star VBN cancel out with this negative IA star VBN. Yay. And we get this negative IC star VBN canceled with this positive IC star VBN. We get this. We're almost there. How do we go from a complex power to a real power? Well, how do we do it here? We just take the IRMS, VRMS, and the cosine of that angle. It's the same thing here, ladies and gentlemen. IRMS of this, VRMS of this, times the cosine of the difference between this angle. Can you see that's why it's okay to mix? Same with this one, ICRMS, VCBRMS, cosine of the phase difference between the two. Nice, nice. Now, is this the power factor of the device? No, it is not. This is not the power factor of the device, so you got to be careful with that. Okay, but hopefully this works out. Okay, what I want to show you is a simulation that kind of, I hope, convinces you that this works out. And what we're going to see in the simulation is that we're going to compute P with the bulletproof way. For a Y, what's the bulletproof way again? Well, the bulletproof way, if we go back to the Y, is what? Let me pull it back. Is this IRMS, VRMS power factor, IRMS, VRMS power factor, IRMS, VRMS power factor. If it's balanced, we're actually just going to take 3 times one of the phases. And we're going to compare it to this. IRMS, VRMS times the cosine of this phase difference and IRMS, VRMS times the cosine of that phase difference. We're going to see that these two are the same. All right. So let's go and switch over to the computer. So share screen, go here. Okay. And what do we have here? We have a 3-phase source, a 3-phase load. And notice I have my A, B, and my CB voltage here. And I have my AN, BN, CN. And I have my A, B, C line currents. And I plotted IA, VAN here, IB, VBN here, and IC, VCN here. And I plotted my IA and VAB here, and my IC and VCB here. And I can run this just for a minute, just so that you can see how the currents are flowing. It's very psychedelic. It's really cool. And so let's just kind of get a handle on what's going on. Notice I have my 3-phase voltage. I have 170 volts max, which means that by the √2 RMS ratio, this should be 120 volts RMS. Do we see that here? Yes, we do, because look at this voltage here and this voltage here. These are 120 volts. Excellent. Okay. I also see I have a 0 phase. I have a -120 phase and a -240 phase offset. So this is a balanced 3-phase system where it's a positive sequence because A leads B leads C. Great, A leads B leads C. What else do we have? If we look closely here, what do we have? We got currents of 0.2 amps or 280 milliamps. Great, RMS. That's what these are measuring. This IA and that IA are the same, and this IC and this IC are the same. Okay, no problem. What else do we see? I'm going to pause it for a minute, and I'm going to look at this ratio here. What do we have? We have that IA lags the voltage. Yep, IA lags the voltage by about 70 degrees. And how do we know this? Well, look at the peak of this guy and look at the peak of this guy. If it were to line up perfectly on that 0, then it would have been a 90 degrees phase lag. Is that correct? If this peak landed not right there on the 0, but it's not. This peak is a little bit before that 0, so it's like between 60 and 80 degrees phase lag. Okay, let's look over this one. Look at this peak and this peak. Well, this peak here is, it's just after, so maybe 5 to 15 degrees phase lag, but the currents are lagging the voltage nonetheless. And why? Because we have an inductive load. Okay, kind of like how we would model an induction device. What about the current here? The current within a phase is, let's see, this peak here and this peak here, maybe 30, 35, 40 degrees, right? If it was 40, so here's your peak, here's your peak and here's your 0 on the voltage. If it was right in the middle, it would be 45, right? But over here, maybe it's 40, right? Okay. So this one's lagging by 40 degrees, this one's lagging by 70, and this one's lagging by 12. Okay, good. We also have access to this nice simulator from Festa. Now, the previous one is open source. Unfortunately, this is proprietary. Okay, so if you're not in this class, I'm sorry, you don't get access to this unless you're willing to pay for it, but it's a really cool product from Festo. And I have exactly the same setup. I have a three-phase load, and notice the values here. I have it at 300 ohms. You see that? I have one click turned on and 0.8 henries. And that is matching exactly with this one, 300 ohms, 0.8 henries. So they're both simulating the same thing. I have this one connected as a Y. Look, I have a neutral connection, and I have the inductor in series with this A resistor, and this inductor in series with this B resistor, and this inductor in series with this C resistor. Good. So I have a three-phase Y load. And what am I measuring? I am measuring here's my three-phase voltage. Line to line is 208, just like we saw before. And here I have ABC. And so the A current, look at this, it's going into this I3 measurement, right? And the A voltage, the A to B voltage is being measured by E1. And what do we have? The C to B measurement, look at this, the blue and gray, is being measured by E2. So that's going to be the 2-watt meter method. And the line current IC is going to I2. So these two, E1, E2, I1, and I2, are measuring what we need for the 2-watt meter method. I am also measuring IA and VAN to do just the bulletproof method, assuming it's balanced, right? These are within the phase. And so I have the neutral connected there and the voltage there. Okay, so if I power this on, I'm going to pause this. Yep, that's pause. I'm going to power this on. And let's see what we get. We get this meter. And I know it's a lot, but let's just look at E1 and E2. That's VAB and VCB, and 216, 208. Yeah, that's great. Look at this, IA and IC 0.28. Yes, that's great. That's actually matching what we saw in this previous one. Look, 0.28, 0.28, and then 208, 208. Okay, so that's good. That is matching this. What else? We can see that VAN is 120 and current IA, well, it's the same as this IA is 0.28. So IAN is this one, 120 and 120. Fantastic. Now, what else does this Festo lab simulation do? Well, it actually gives you the phase change. Check this out. The phase difference between the voltage and current of this AB and IA is 72 degrees. And that is what we see here. The phase change between the E2 and I2, which is BC, VBC, and IC, that is 12 degrees. And that's what we see here, 12 degrees. Fantastic. And the phase change between the IA and VAN over here is 42 degrees. That's fantastic. That's right here. Okay. And what's cool is actually the Festo software actually shows this on a phasor plot as well. And so here's a phasor plot. So you have AB, and look at this, the current 72 degrees. See the current here, IA, and you see a 72 degrees phase lag. Boom. You have the VBC and the IC. Look at this, VBC and the IC. And look at the difference. It doesn't have the number quoted, but look, it's about 12 degrees. And then the last one, you could look at the AN, which is this guy here, and the IA, and it's about 40 degrees, right? That's kind of nice. And the other thing to note is look at the magnitude. The magnitude of the voltage of the AN is √3 smaller than the line-to-line voltages. So you're seeing consistency on the phasor plot, and you're seeing consistency on the metering, right? And you can see the oscope values down here. All right, this is great. So what about power? You promised me power. So, okay, sure. The power, the real power is RMS of this times the RMS of this times the cosine of that, which Festo does that. It's 25 watts. And you could do that. You could take 124 times 0.27 times the cosine of -42 and you get 25. And what is 25 times 3? Well, we can pull up our calculator. So let's do that. So calculator. Okay, and we can say 25.7 times 3 is equal to 77 watts. So this load is burning off 77 watts right now of real power. Okay, now let's look at this one. So over here, what do we have? We have the phase differences here. So we take the RMS of this times the RMS of this times the cosine of -72 becomes 18. Okay. And then we can say that the RMS of 216 times the RMS of 0.27 times the cosine of negative 12 equals 58. And you can easily see now, look, 18 plus 58 is 77. Do we get a match? Yes, we do, ladies and gentlemen. This is nice. This is consistent. Okay, so this is the benefit of the 2-watt meter method. Now the question is, well, what about S? What about the apparent power? Can we do the same thing? Can we get the apparent power for these two guys and add them up and just get it? Or can we take the apparent power of this one and multiply by 3 and get it? Well, this one for sure. Look at this. Assuming it's balanced, yes, we can. I have this times this. I can just click this button. The apparent power is just this times this. It's the RMS of it's 124 times 0.278 becomes 34. You can punch that in your calculator. Okay, what about this one? We can say, well, what number is that, by the way? So 34, let's do it. 34.82 times 3 equals 104. Okay, so the apparent power should be 104. Okay, that means it's bigger than the P. That's good. Okay, what about over here? Check this out. This actually gives you this. Oh, so if I take the RMS of this times this, well, it's already an RMS, I get 60 and 60. Wait a second. 60 plus 60 is 120. That does not measure or match 104. What's wrong? Does the 2-watt meter method not give us apparent power? Well, that's not quite true. That's not quite true. It does, but we have to account for the fact that there's a phase angle difference. And let's go back to the DocCam to see. Okay, so if we go back to the DocCam here, and so the question is, well, what about the total apparent power, right? Okay, so the total apparent power is from what? Well, we know it's the magnitude of the complex power, right? And if it's balanced, then what? Then we can just take 3 times the RMS and VRMS of just one phase. That's no problem. Yay. Okay. And it should be 104, right? But we can't just do that for, I mean, you already saw it, right? You're getting 60 and 60. That doesn't work out. You're not getting the same answer as this one, right? Even if it is balanced, okay? We need to account for the power angle. So let's just kind of work out examples. So I pulled the numbers down. 216 for the line-to-line voltages and 124 for the line to neutral. Okay, bigger, yep. IA and IC 0.27, good, that's the current. We wrote this down, theta V minus theta I is 72 and theta V minus theta I for the C is 12, good, right? If I took 3 times the IRMS, VRMS of the line to neutral, I get 104, we already showed ourselves that. Right. Now, what about the S? Well, we know S, the total, is going to be the magnitude of the vector addition, not just the addition, the vector addition. And we saw the magnitude. It was 60. 60 with an angle of 72 and 60 with an angle of 12. And you guys can remember in your head, 60 with an angle of 72 plus 60 with an angle of 12. Yeah, if they were in the same line, you could just add them to get 120. But not if they're vectors like this. You actually would get something like this vector, and check it out. The number would be 104 with an angle of 42. Nice. So 60 plus 60 is not good. Now, let's say you're like, well, how would I get that? Not too bad. If you have a TI-89, we can do it. Watch this. So 60.31, and I can use the angle symbol here. Okay, there's my angle symbol, right? And I can put 72 degrees, 72.31 degrees, plus 60.31. Notice I got to put the parenthesis there, times 60.31 with an angle. I can use that angle command, and I'll put 12 this time, 12.31. Okay. I can get that, and look, it gives it to me in rectangular form, right? 77 and 70i. Okay, no big deal. We can handle that. So what I can do is I can go to hit catalog, so catalog here, and I can find the ABS, absolute value, which is the magnitude, and I can bring this answer in with a parenthesis. Look at that, 104, perfect. I can also take and get if I want the angle, I can go to catalog again and hit angle. You can see angle there, okay, hit angle, bring that answer back in. close it off with a parenthesis, excuse me, and I get 42 degrees, 42 degrees. Fantastic. So now you can see consistency between the 2-watt meter method and the bulletproof way, assuming it's balanced, right? Okay, so let's go back to the Festo and make sure that's all correct. So I'm going to go back and share screen. So check this out. I have 60 plus 60. I know it's wrong to just add them to 120, but here's the cool thing about Festo. It will know that this is a, what do you call it? This has some issue in it, right? It has a vector because it's looking at E1 and E2 and I1 and I2 in its entirety. If I click S, it gives me 104, which is 3 times this answer here. The 3 times is 34. Beautiful. We get consistency. Okay. I apologize that for those of you watching without this Festo software, you can't access, but I will at least put this link in the description so that you'll have this. Okay. All right. Well, I hope this lecture was educational and you learned a lot, and we'll see you in class. Okay. Take care, everyone. Bye.